So we are live. Is anybody in both the YouTube and the Etherpad? Hi, Philip and Micah, and possibly Andrew. Can you hear me? Excellent. So if at any point we have issues with the audio, please let me know. I obviously can't tell if you guys can't hear me. I'm on a hotel's Wi-Fi right now, so they may, get mad at me and somehow throttle me a bit. So please let me know if there are any issues at all. So what we're going to do is I'm basically going to run the review session with GIMP, which is kind of like Microsoft Paint for those of you who are not Linux users. And that way it's kind of like a whiteboard. I can draw on it and answer your questions. And then because it's a little harder to raise your hands and have me call on you over the internet, I've set up the Etherpad for you guys so that you can type questions to me and I can read them and I'll read them out loud for those of us who aren't with us live, and then I can answer them. So with that being said, let's go ahead and get started. What do you guys want to work on first? Our topics covered in the exam are going to be context-free grammars, the Pushdown automata, pumping lemma for context-free languages, Turing machines, and I'm missing one thing. Let me see what it is. Oh, and Chomsky normal form for context-free grammars. So those are your options. Where should we start? All right, so I'm getting pumping lemma, Turing machines, and closure proofs. So let's start with the pumping lemma for CFLs. So would anybody like to give me a language that I need to prove is not context-free using the pumping lemma? It can be from your homework or the book or any other examples that you have run across that you're not sure how to do. I believe the one in the homework was L equals WW such that W is in sigma star. Zero. So let's go through that example, and then if you have other examples that you would like me to work on for the pumping lemma, you can let me know. So our language is L equals WW such that W 0 star 1 star, and we want to use pumping lemma to prove this is not a context-free language. So first we want to start with, so this is the same game that we played with the pumping lemma on the first test. So our opponent is going to say for all P, and we want to pick a string that does fit into this language. And the this is really where the hard part comes in. This is really where you have to do your thinking, is figuring out what kind of language can I use to prove that this is not context-free. So for example, if you picked WP, or I'm sorry, 0 to the P1, 0 to the P1, this would make things extremely difficult, because what you're going to end up doing is you're going to say for all U, V, X, Y, Z, S can be broken into U, V, X, Y, Z, such that V, X, Y, the length of that is less than or equal to P, and either V or Y is not the empty string. So this string looks like it would work pretty well, but then you may get into the issue of, you can break it down into some number of zeros for U, followed by some number of zeros for V, followed by a 1 for X, and then some number of zeros for Y, and some number of zeros, or I'm sorry, and a 1 for Z. And then you run into the issue of, if the length of V, which is all zeros, equals the length of Y, which is also all zeros, and you take your new string is going to be U, V to the 0, X, Y to the 0, Z, then you may have an issue where S me scroll down a little bit here. Where your new s new, can still equal 0 to some number 1, 0 to some number 1, which still equals WW. So in that case, you haven't actually proved what you're trying to prove using the pumping lemma. And so you need to reconsider this string right here. So we need to choose a better string for that. So what we can do instead, I'm going to choose a new color, is, again, our language here is L equals WW such that W equals 0 star 1 star. What we can do instead is say for all P, we have some string S that equals 0P, 1P, 0P, 1P. And then our opponent is going to say for all U, V, X, Y, Z. I think there should actually be a W in there somewhere, but it doesn't matter what we call our variables here. S equals U, V, X, Y, Z such that V, X, Y is less than or equal to P, and either V or Y is not the empty string. So what we can do again is we can make a new string, and we basically want to pump V and Y here. So we're going to say U, V to the K, X, Y to the K, Z. And we want to generally choose K to equal 0. That's the general rule for pumping lemma for context-free languages. Now, the pumping lemma that you saw in the first test, if you set K equals to 0, you actually ran into problems, and some of you may have lost points. But in general, it's okay to set K equals to 0 in the pumping lemma for the context-free languages. So anyway, here we have a few cases that we need to consider. So case number 1 is if, let me scroll up just a little bit so you can see our string. There you go. Case number 1 is if V, X, Y is all strings in the, so you can have either all zeros in the first one here, so that would be if U equals 0 and Z equals 1 to the P, 0 to the P, 1 to the P. In which case, if you pumped, if you had U, V to the 0, X, Y to the 0, Z, then you would only be removing zeros from this part right here, in which case you would no longer have WW because this 0 would be less than this 0. You could do the same thing for basically any combination of these things. So VXY could be zeros in here. It could be zeros in here. It could be all ones, in which case we'd have the same thing. Or it could be some combination of zeros and ones. So if, for example, your VXY was like in the middle, where you have some number of ones followed by some number of zeros, and still the length of VXY is going to be less than or equal to P, then you would be effectively taking out ones from right here and zeros from right here, in which case, again, you would no longer have WW because your new string would be 0 to the P, 1 to some number n, where n is less than or equal to P, just less than, not equal to, some number 0 or to the n, where n is less than P, and then some number 1, 1 to the P. And so again, you would not have WW because this number of zeros would not match this number of ones would not match this. So that's basics of pumping lemma for that particular language. Any questions about that? Sam, can you hear me? Are the drawings clear for everyone? Are there any issues? I know my handwriting is a little messy, especially considering I'm using a tablet here to write, but is everybody okay? All right, are there any other examples you would like me to do for the pumping lemma? Okay, give me the different language, Sarah. So Sarah says that she has a question about a different language for the pumping lemma. And she's typing that up for me right now. All right, so Sarah's question is about the language WW, where the second W is reversed, and W can be anything in AB star. So let me write that on here. I'm going to go ahead and erase all this. Again, remember that this is live right now, but if at any point you feel like you need to go back and look at some things that I wrote down, the video will be posted on YouTube in its entirety after the review session is over. So I'm going to erase everything here, but please feel free to look at it after the review session is over if you need to. Okay, so Sarah's is L equals W W R such that W is in sigma star. Our sigma is going to be AB star. And WR just means it's the reverse of W. Okay, and Sarah says, someone on Reddit asked a question about his string A to the P, B to the 2P, A to the P, but I didn't think that would work. Others said it would, so I'm not sure now. All right, so let's talk about that. So again, we have for all P, that's our rule, and we want to say there's some string, and the string that Sarah gave us is A to the P, B to the 2P, A to the P. And you can see that this takes the form of WWR because if you have W equals A to the P, B to the P, then WR would be B to the P, A to the P, and so WWR would be A to the P, B to the P, B to the P, A to the P, which is the same as A to the P, B to the 2P, A to the P. So we want to split that up. So again, remember our opponent is going to say for all U, V, X, Y, Z, such that our S equals UV, oops, that's not a V at all, UV, X, Y, Z, such that the length of VXY is less than or equal to P, and either V or Y or both is not the empty string. So we get to choose, so this is where we pump. So our S new is going to be U, V to the K, X, Y to the K, Z. And we want to generally choose our K to equal 0. So now we need to figure out what can VXY be. Let me see if I can scroll so that our example language is still up there. We still have some room. Okay, so what can VXY be? So since VXY has to be, the length has to be less than or equal to P, we have a few cases again. I'm going to choose a new color for our cases, make it a little easier to read. Case 1 is that VXY could be all A's. So it could be in this, or it could be in this. Either way. In which case, if we had U, sorry, that's a terrible U, U, V to the 0, X, Y to the 0, Z. If it's in the first one, then we're going to have A, if U is A, some number of A's, and then let's say V equals A to the N, we're not going to have that anymore. And we'll say Y equals A to the M, not going to have that anymore. So we're just going to have some number of A's that is less than P in some way, and then Z would equal, X would also equal an A, and then Z would equal the rest of it, so B to the 2P, A to the P. So we'd have some number of A's that's less than P, B to the 2P, and then A to the P, and so this number of A's would not equal this number of A's, and so this cannot possibly be WWR because there's nothing that W can equal that would allow A to some number that's less than P, B to the P, be reversed as B to the P, A to the P. You can't do that. So that's one case. Our second case, and that again, that works for either side of those A's. So it works if it's over here, and it works if it's over here. Our second case could be if, so let's say if VXY is all B's. So let's talk about that. That's where things might get a little bit interesting, in that you may not be able to prove it with this. So if it's all B's, then U, V to the 0, X, Y to the 0, Z would be A to the P. And we'll say V was B to the N and Y was B to the N. So let's assume that they're the same number of N's, or sorry, same number of B's. Then we would have b to the 2p minus 2n. And then we could have a to the p. And here we may run into an issue because this right here will still be an even number of b's. And so regardless of what this is, let's say 2p minus 2n equals 2m, we would get a to the p, b to the 2m, a to the p. And that could equal WWR if W equals a to the p, b to the m. So it sounds like, Sarah, that the person on Reddit that you were talking about who said that it wouldn't work is actually correct. So it looks like in most cases, this would work if BXY was all A's, or if it was some combination of A's and B's, that would be fine. But if it's all B's, and in the case that V and Y are the same length, they have the same number of B's in them, then pumping V and Y like that will not work. It will still give you a string that is in that language. So I'm not actually sure if that language, Sarah, is context free or not. I haven't seen it one way or the other. I could research it. But just based on that, I'm sitting here trying to think of strings that would work if we pump them. And I can't immediately off the top of my head think of anything that would prove that it's not context free if we could pump it. So if anybody has any ideas about some other string that we could pump and show that it's not context free, by all means, let me know. But that one may not prove to be, it may not prove to be possible to prove with a pumping lemma, and it may even be context free. I'm not honestly sure. I'd like to think that it's not, but I have a hard time coming up off the top of my head with something that that would work with the pumping lemma. So other questions about the pumping lemma for any of the languages? I don't remember if one of the 3 languages that CIPS approved, if it was one of those. I'm pulling it up right now to see if it was one of those 3 languages, in which case I can look and see which languages those were. Let me see. Yeah, so it's not in any of the 3 that CIPS approved either. So anyway, any other questions about pumping lemma before we move on to another topic? And I apologize for the people who are not watching this live. It looks like about a 1 or 2 minute delay between when I say things and when you guys hear them. And so I'm basically sitting here and waiting for you all to hear my call for new questions so that people have time to type up their questions after they hear it. Oh, Dr. Sullivan just said that language is context-free. So the pumping limo won't work. Thanks, Dr. Sullivan. I didn't realize she had joined us. Okay, so if there are no other questions, what would you guys like to tackle next? Philip asks, is there any problems with number 1 or 2 in this pumping lemma? Philip, what do you mean by number 1 or 2? So yeah, in that pumping lemma, there was a problem if BXW equaled all B's, because in the one specific case where V and W, which are the two variables that you would be pumping, if those two variables had the same length, so if they were all B's and they were the same number of B's, and you pump them to 0, which means you took both of them out, then you would still have an even number of B's. So you'd have A to the P followed by some even number of B's, some number that could be divided by 2, followed by A to the P. So you would still have WWR, where your W would be A to the P followed by some number of B's, and then your WR would be the same number of B's followed by A to the P. So yeah, that is problematic. And as Dr. Sullivan said, the language that we were trying to do the pumping lemma on is context-free, so the pumping lemma won't work, and there's no way to prove that it's not context-free because it is. Other questions? Pumping lemma or any other topic? All All right, let's tackle Mr. Pushdown automata as Sam has requested. So, our Pushdown automata basically uses a stack, and a stack is just, and I'm sure you've seen this drawn in other classes. It's diagrammed like this, where you have some number of elements that you can push onto the stack, and you start at the bottom. And when you push something onto the stack, it goes right here, and this is called your pointer, right there. And whenever you push something onto the stack, you push it so it stays right here, and then you move your pointer up. And you keep doing that for as long as you're pushing, and then whenever you pop something off of the stack, then what you want to do is move your pointer, so move your pointer down, so your pointer is now right here again, and you want to take this off of the stack, so there's no longer an X here. So that's the basics of, very, very simple, in very simple terms, how stacks work. And so our pushdown automata reads through a string using a stack to make sure that that string, usually you want to see, I have the same number of X's as I have Y's, or something like that. It's usually to show that you have some same number of one thing as you have of the other. And so what you can do, let me see if anybody has given me a specific language. All right, nobody's given me a specific language, so I will just make one up. And I will try not to make one up like I did with Crystal, where I made up an impossible language. So let's do, the language is going to be W is A, B star, such that the number of A's is twice the number of B's. So that again is number of A's is twice the number of B's. So let's do a pushdown automata for that language. So what we want to do, and I'm going to draw this out and just sort of think it through before I start actually drawing out the automata, the diagram, is let's say, so we have two cases. Case one, we start with an A. And case two, we start with a B. You always want to consider, what can I start with for pushdown automata? Some languages will say you can only start with an A, or you can only start with a B, or a 0, 1, or X, Y, or whatever. But some languages like this one, you can start with both, and that's where it gets a little more complicated, because you have to consider both of your options. So let's say we have case one, where we're starting with an A. So if we see an A, then we want to push. So we need to have twice the number of A's as the number of B's. So if we see an A, then we want to push AA. And what that does is it says, okay, when I see a B, I can pop one of these A's, and then when I see another B, I can pop another A, and that ensures that I will be able to have twice the number of B's as I have A's. So if I see an A, push AA, and if I see a B, pop an A. Okay, and then our second case here will be if we start with B's, and we're going to go back and forth between these cases throughout the automata itself, and I'll show you how that's going to work. So if I see a B, I need to push something, and I need to make sure that I have twice as many B's as I have A's. So I'm going to push one B. Let me see. And then if I see an A, I basically want to be able to pop two Bs, but that's not always going to be possible. So if I see an A, I either want to pop two Bs, BB, or if I only have one B to pop, I want to pop a B and push an A, which again would give us, making sure that, so if we take this rule right here and combine it with this rule right here, then that would say, okay, I see an A and I want to make sure that there are two B's to go with it. So here's one B to go with it right here. And if I don't have another B to go with it yet, I can push down an A. And once I see another B, I can pop that A and that will be okay. So those are our two cases, or our basic rules that we want to deal with. And so now we need to change that into an automata. So an automata is just, like your finite state machines, in that you have your starting state. And I apologize in advance if this gets a little messy. So since we have two starting cases, we can either start with an A or start with a B. We need to make sure that we account for both of those. So first we need to initialize our stack. Let's do that first. So we see lambda. We want lambda to go to Z0, which is initializing the stack. This will be Q0. And once we have initialized our stack, so I'll draw our stack up here. Just for an example, this will be Z0. Our pointer is going to move up. So if we see an A in our string, then what do we want to do? Let's scroll up a little bit. We want to push AA. So lambda will go to AA. This will be Q1. And we can do that as many times as we want. So every time we see an A, we push two A's to make sure we get twice the number of B's later on. And then our other starting case was if we see a B. So if we see a B, then we want lambda to go to B. And that's going to be Q2. And again, we can do that as many times as we want here. B, lambda goes to B. And now here's where things get interesting. So if we're in this state and we see an A, we need to either pop two B's or pop a B and push an A. So let's say that, let's just start with popping the one B so far. So if we see an A, then our 1B is going to go to lambda, and that'll be Q3. That's a 3. And then in order to deal with that second B there, we basically can just have a move on lambda. So either lambda, if we have a B, B goes to lambda, or lambda, if we don't have a B, then we need to push an A. So that would be lambda, lambda goes to A. And that's going to be Q4. And I'll draw this over here a little better. This is an A. And then we want to go we want to make sure that we can go back and forth between Q2, Q3, and Q4, and possibly even Q1 as much as we need. So if we are in Q4 and we see, so we have either just popped a B or pushed an A, and let's say that we see we're going to have to make Q4 two different states, actually. So let me delete this. I apologize for the confusion. So we're going to need a state for if we need to pop another B, or if we need to push an A. So here's if we need to pop another B. B goes to lambda. Here's if we need to push an A. So lambda goes to A. This will be Q5. This will be Q4. And this may get a little bit hairy, and I apologize for that. I'm drawing this from scratch. So anyway, so here we have pop two Bs, and we have some number of A's or B's on the stack. We're not necessarily sure what we have exactly. So we can say that, we can say two things. So we can say either we see a B from here, or we see an A from here. If we see a B from Q4, then we can go back here. So if we see a B, lambda goes to B. Or if we see an A, it's a terrible arrow. We see an A, lambda can go to AA. And we can also have, if we see an A and we still have B's on the stack, then we can go here, where A, if we see an A, then B goes to lambda. So it's getting a little messy, but that's okay. So far, just to summarize, we have the starting state. If we see an A, we push two A's, and we can do that as much as we want. We haven't dealt with what happens after that. We still need to do that. We have in the starting state, if we see a B, we push a B, and we can do that as much as we want. And we have dealt with how we deal with A's and B's from there. So if we started with a B and we see an A, we want to pop that B. And if there are two B's to pop, which would be right here, then that would be, we need to pop both B's. So on lambda, we pop the second B and go into Q4. But if we are in Q2, we see one A, we pop the B, and then we don't see another B, then we need to push an A. So we have dealt with what happens with this B over here and these B's so far. All right, so let's deal first with Q5, and then we'll also deal with Q1. So Q5, we need to go over here if we see another A. So we've popped one B, we pushed an A. If we see an A, and lambda, we need to push two more A's so that we can pop B's from there. If we see, so if we're here and we see a B, if we're in Q5 and we see a B, then we just need to pop that A that we just pushed. And that will take us back to, at that point, we will have empty stack. So Let me make sure I'm doing this right. I think that I am. If we see a B, we need to come back here, B, and we need to pop that A that we pushed. And that will just take us back to Z0 in that case. And so we'll go back up to Q0 and start over from wherever we are. Now let's deal with Q1. So Q1 is where we have seen an A and we pushed two A's, and we want to now make sure that we are popping enough B's to deal with all of those A's. So this might get kind of gross. I'm going to delete this so we can have some more room here. Okay, it's a little better. So we're in Q1, and we've already got it so we can push as many A's as we want. We need to start popping some B's. So there's not really a good exit out of Q1 here. I'm going to just draw it up here. Okay, if we see a B, then we want to pop an A. And this is Q6 is what we're at right now. And we can pop A's for as long as there are A's. So if we see a B, keep popping A's. And then if we run out of A's to pop and we're still getting B's, then we can go down here. So this is if we see a B and we've run out of A's to pop, then we need to push a B. Or if we're in Q6 and we see more A's, then we just need to go back to Q1. And again, there's not a good way to do this, and I apologize for how gross this is, but if we see an A, we need to push two A's and just go back to Q1. So I believe that would be our final pushdown automata here. Does anybody see anything wrong with it? Let me switch back over here to our Etherpad so I can see what questions or statements you have come up with so far. So Micah is correct in saying that PDAs are based on non-deterministic finite automata. So you don't have to have a trap state. Basically, if you're in a state and you don't have a transition for what you are trying to do. So if for this particular thing, since we're using sigma star, there's nothing really that that would come up. But if you're somehow in a state and you see some character come up and you don't have a transition in that state for that character, then it automatically goes to what's considered a trap state and the machine dies because you don't have a transition for that. Philip, if you start off with the B in this language, it doesn't automatically go to a trap state because I made it so that it could be sigma star, which means that you could have some number of A's followed by some number of B's followed by some number of A's, some number of B's, et cetera, as long as you want. Or you can have same thing but opposite, so some number of B's followed by some number of A's followed by some number of B's, et cetera, et cetera, et cetera. Made it a little more difficult on myself using sigma star, drawing the pushdown automata than if I had set a little more restrictions on the language, but that's okay, not a big deal. Philip, to answer your question, lambda is if you're in the stack and your pointer is pointing to sort of an empty space in the stack. Lambda is the same as epsilon, so it just means that it's empty. And Z0 is where you have initialized the stack, and that's how you make sure that you've gotten down to the bottom of the stack. So I do need an accept state. You guys are correct about that. So let's talk about our accept state. This is going to be not a lot of fun. So let's see. I can scroll over a little bit here. All right, so if we're in Q1, we pushed a bunch of A's and then we popped a bunch of B's, so we can get to an accept state from Q6 if we have reached the bottom of the stack. So if we see Z0, we want Z0 to go to lambda, and that means we've reached the bottom of the stack. There's nothing else left to be read in, and this is our accept state. We can also get to the accept state from, let's see, we can't get to it from Q2 because that's only if we have pushed a bunch of B's. We can get to it from Q5. So if we have pushed exactly, if we have pushed exactly 2 B's, for example, in Q5, and we see Z0, then Z0 can go to lambda, and that would be acceptable. Sorry, that's not correct, not Q5. Let me delete that. Q4 is what I meant. Q4. So Z0, and then Z0 would go to lambda. And that will work. We might have an issue with this transition right here. I might need to delete it. Let me delete this transition. I've made this unnecessarily hard on myself, and I apologize. That eraser is way too small. Let's make it much bigger. Yeah, let's delete all of that. Okay. All right, and then let's redraw these lines. Here, 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 here. All right, so if we're in Q4, and we have 2 B's, we've popped 2 B's for our A, and then if we see another A, we can either, if we are at the bottom of the stack and we see another A, then we go back to Q1 like that. But if we are not at the bottom of the stack and we see an A, then our A needs to pop a B. Is this the same transition that I just had? A, B goes to lambda. Is that correct? I'm sorry if that's the same transition I just had. Anyway, so B would go to lambda, and then we'd pop 2 B's, so we'd have this lambda transition right here going into Q4. Q4, if we reach the bottom of the stack, we can accept it from there. Where else can we accept it from? I don't think there is anywhere else. Nope, I don't see anywhere else. So that should be our actual final Pushdown automata. So Phantom, which is probably not his real name or her, is asking, can there be more than 2 B's for each A? So our language, let me scroll over here for you, was W is in sigma star, where sigma is just A and B's, such that the number of A's is exactly twice the number of B's. So to answer your question, no, there cannot be more than 2 B's for each A. We have taken care of the idea of, I'll scroll down here again. So we have taken care of the idea of if we have several B's here, so if we have a B here and then more B's here, what can we do? So let's say, for example, we have 4 B's or 5 B's or some number greater than 2. Then we see an A, so we want to, from Q2, go to Q3. So we pop 1 B, and then we have a lambda transition, an epsilon transition from Q3 to Q4 where we pop a second B. So that just says every time we see an A, we need to pop two B's. And the way that we can do that is using A, B goes to lambda, and lambda, B goes to lambda. So that pops two B's. And then if you see another A, you continue to do that same thing until you run out of B's, in which case you start pushing A's instead. So you can have, like 5 B's followed by 2 A's, followed by, so that would pop 4 of your B's, and then you'd be down to 1 B. If you want to push another A from there, then what you would do is you would go, you would, from Q4, you would pop that last B, the 5th B off, and then from Q3, you would go to Q5. And so you would have lambda, lambda goes to A, where you would be pushing another A to show that you have one A that is not accounted for so far. So basically you need half a B, but that doesn't make any sense. But that's effectively what you need. Start state should be a final state, absolutely, Andrew, because we can have the epsilon string here. We can have the empty string. So we'll make start state a final state. And we go through the route where we get a B without any A's on the stack. I get how when we get an A, we push AA, so we get a B, we remove an A as counter, but in the case where there is no A and you see a B, I'm a little confused. Okay, so yeah, we can go through that, and I will pick a different color so that you can actually see me going through that. Let me pick a different color here. So we are in Q0 right here, and you want to know about when we get a B, but there are no A's on the stack. So if we see a B right here, then we just want to push a B, okay? And we can do that as many times as we want. But let's say we only push one B. So if we get an A now, we can't pop two B's because there aren't two B's to pop. So what we need to do, if we only have one B, we go right here, and we say A and B goes to lambda, so that's popping that B. And then we can't go here. No, we can't do that because there's not another B to pop. So what we need to do instead is do this transition where we need to push down one A. And this says, okay, I have one B and I've seen an A, so I need to really have two B's, but I only had one. And so I pop the B, and I'm left with, I'm at the bottom of the stack, I'm left with lambda, so I pushed one A. And what I can do from there is if I see a B, if I'm in Q5 right here, and if I see a B, I can pop that A, and that ensures that I have seen two B's for every A, and I can just go straight back to Q0 and start over. Or if I'm in Q5 and I have one A already and I see an A instead, then what I want to do is push two more A's. So now I would have, for example, 3 A's on the stack, which means that I've had one B, I've seen one A, and here I have, I need to make sure that I push another A, so I see a second B somewhere. And here, if I see another A, then I need to make sure I get 2 more B's. So altogether, I would need 3 B's. And we come over here to Q1, and Q1 says that for every B we see, we can pop A's. And so we can keep doing that. We get 3 more B's, we can pop them. If we get A's, we can push A's and go up into Q6 and then pop them from there, etc. Does that answer your question, Phantom, whoever you may be? So Sarah has it right. If there's no A and just B's, it stays in Q2 until we start reading some A's. Go a little bit so you can see most of the graph here. Any other questions about that or about any other pushdown automata you would like me to work through? If there's not, we will move on to another topic. So if it's a BBA phantom, what will happen? So you're right, I did the case BA. So if it's BBA, I'll pick another color. Let's make it blue. Let's make it orange. So if it's BBA, where is my cursor? There it is. So we're going to start here. If it's BBA, so we see one B, and we move here into Q2. Then if we see another B, we stay here, we stay in Q2. So now we have two Bs on the stack, and now we see an A. So if we see that A, we move into Q3, and we pop one of those Bs. Now Q3 lets us do some lambda or epsilon transitions, in which we can either pop another B or we can push an A. Since we have another B on the stack to pop right here, we can do a lambda transition to Q4, and that would leave us at the bottom of our stack. And so if there's no other character to read in the string, we can go straight to the accept state. Again, any other questions about that? No, it should not be BB because there's no guarantee that if we see one B, we are going to see a second B. Now, I am using a different notation than Dr. Sullivan uses, and I actually do that a lot with a lot of these problems that are going to be on this test for some reason. I just learned them a different way. So you guys have learned this notation that says if we see a B, then B goes to BB, and that's fine. But I'm just using a different one. So I'm saying if we see a B and we are at a point in the stack where we have lambda, then that lambda goes to B. It's the same thing. These two things are equivalent. I just use a slightly different notation. So I apologize if that's confusing you. And if you really want me to, I can redraw this entire pushdown automata with Dr. Sullivan's notation instead of mine. Okay. So any other languages you would like me to do a pushdown automata for, or if not, where would you like to go from there? So we have done so far pumping lemma for CFLs. and we have done Pushdown automata, although of course, if at any point someone joins us and wants us to cover more about those, by all means, let me know. So I'm going to write in our Etherpad, please let me know if you want more covered. And I will strike out that last part. And same for here. Please let me know if you want more covered. Right there. There we go. All right, so Philip Bailey, very easy. Some tips on identifying ambiguity. This will not work all the time, but it will work most of the time. Let me delete all this. And again, if you are watching live and you want me to, you feel like you missed something that I just deleted, please feel free to go back and watch the YouTube video after we're done with the live session. Everything's being recorded, so you can go back and see what you may have missed. So anyway, here's how to determine ambiguity. So let's say you have some language. I can't remember what languages, and I'm going to pull them up because it may actually be helpful to walk through the languages that Dr. Sullivan put on your homework. And I believe that was homework maybe 8 or 7. I'm pulling it up right now. It was not 7. 7 was all Chomsky normal form, so it should be 8 that we looked at. Nope, it was earlier than that. Okay, so this is homework 6, number 3, and I will just work through all of these examples because they're all very, very good for quick tips on how to determine if a language is ambiguous or not. So first one is L equals, oh, we don't even have an L, we just have a production rule. So our first one is S goes to ASBS or epsilon. And we want to know, is this ambiguous or not? And here's our quick tip for Philip. Basically, what you want to do is determine what are the combinations of characters that I can have in this production rule here. So I can have, obviously I can start with A, and if S goes to ASBS here, then I can have an A followed by an A. If this S right here goes to epsilon, then I can have an A followed by a B. And then I can also have some B's followed by some other thing. So if this S right here goes to ASBS, then I can have a B followed by an A. Or if that S right there went to epsilon, let's see. If I had B goes to ASBS, then I can have B followed by an A. Or if it went to epsilon, it would just be B. I don't think I can ever, no, I can get a B followed by a B. I'm sorry. If this S went to ASBS, so I would have ASBS, this S goes to ASBS, that would go to ASBSBS. And so if this S went to epsilon, then I would have right here a B followed by a B. So those are the combinations of 2 different characters in order that we can have. We can have either an A followed by an A, we can have an A followed by a B, we can have a B followed by an A, or we can have a B followed by a B. And again, this is just quick tip. This will not work 100% of the time. It will work like 99% of the time. So what my quick tip is to figure out, are there two ways to get any of these combinations of letters? I'll give you a hint. For this one, it's not going to work. So if we want an A followed by an A, we can either have, so we have ASBS, and this S goes to ASBS, so that will give us AASBSBS, in which case we have that right there. And there's no other way for us to get an A followed by an A. If this S went to ASBS, then this A would be followed by an A, but that's the only way we can get an A followed by another A. So let's look at an A followed by a B. So if we have ASBS, and this S went to epsilon, then that would give us ABS. And again, there's no other way to get an A followed by a B. So, we could do the same thing. So if this S went to ASBS, then that would give us ASB, oh, sorry, that's not right, AASBS, BS, and then we could have this S go to epsilon, and that would give us AB right here, but it's still the same thing. This S has to go to epsilon. This S has to go to epsilon. There's no other way that we can get an A followed by a B. So I'm going to delete that because it's kind of in the way. So now let's look at B followed by an A. So we have ASBS, and if this S went to ASBS, then that would give us ASBASBS, and we'd have this B followed by an A. And again, there's no other way to get a B followed by an A. And so, no matter what you do, if you want a B and then you want an A to follow it, you're going to have to turn this S right here into ASBS. And then for BB, so we can start with ASBS. The only way that we can get a B is if we take this S and try to turn it into ASBS, it won't work because that's what we just did right here. And that just gives us a B followed by an A. So we have to take this S and turn it into ASBS. So that'll give us AASBSBS. And then our only way to get a B followed by a B is to take this S and turn it into epsilon. And that'll give us AASBBS. So there's our B followed by a B. And that's the only way you can do it. You can have any combination of these ASBS that you want, but to get a B followed by a B, this S right here at some point has to turn to epsilon. So that's just a quick tip. And in this case, you can see that it's not ambiguous because there's only one way to get each combination. And I say that that's a tip and it works 99% of the time because there is a language that this does not work on, and I'll talk about that in a second, but let me go through the next few examples here. So that was this was 3.a. Let me make sure nobody has any questions so far. So L view, I'm guessing that's Linda. Those are just the possible combinations, the AA, AB, BA, and BB. Those are just the possible combinations that we can have of one character followed by another character. Thank you, Sarah. Okay, so let's do 3B. So I'm going to scroll down, and I'll do 3B in a different color. Let's do it in yellow. All right, so 3B. The production rule for 3B was S goes to ASBS or ESAS or epsilon. And you can probably pretty much right away see that this is ambiguous, but let's walk through the same thing. So what are all the combinations that we can have of one character followed by another? We already know because we just did this one in the last example that our combinations are AA, AB, BA, and BB. And we just want to prove that there's a way to get one of these, any of these, like I said, any of these, that there's more than one way to get that combination. And again, this is just quick tip. This works like 99% of the time. There is a language that this doesn't work on, and I will show you what to do with that language when, after I do the three examples here. So to get AA, we can either have, so we can start with ASBS, and this S can go to ASBS, in which case we'd have AA, SBSBS, and here's your AA there. Or we can start with BS, AS, and this S could go to ASBS, and that would give us BS, ASBS, and there's your AA right there. There is two different ways to get AA. And we can stop right there. We don't have to go farther because we've already found that this language is probably ambiguous. And I will write that word in all caps, probably ambiguous. How do we prove that it is definitely ambiguous? What we need to do there is we need to actually pick a string that is in the language and show that there is two ways to create that string. So I will create the string, and this is, you just have to kind of be smart, and it might take you some time. You might just have to play around with this, but let's create the string AB, AB. We need to show that there are at least two different ways to prove that it's definitely ambiguous. So here's number one. Let me scroll up so we can see our rules still. Okay. So here's number one. If we have ASBS and this S goes to epsilon, then that would give us ABS. And then we can have this S go to ASBS, which give us AB, ASBS, and then both of these S's would go to epsilon. That would give us AB, AB. So there's one. What else can we do here? Two. If we have ASBS, and let's say that this this S goes to BSAS. So that would give us ABSASBS. And then all we need to do is have this S and this S and this S all go to epsilon, and that would give us AB, AB. So there you have it, two different ways to show two different ways that you can create this string ABAB that is in the language. And so this example is definitely ambiguous, and that's the only way to actually prove it. So this stuff that I did up here is just for probably ambiguous, not definitely ambiguous. So that's just a quick way to show that it is probably ambiguous, and in order to prove that it's definitely ambiguous, you need to have a string that you can create in two different ways using the rules. Okay, now let's do 3C, and then I will show you a language where it is probably ambiguous, but you can't actually prove that it's definitely ambiguous because it's not actually ambiguous. So let me do 3C, and then I will show you that one language that I came up with. So let's delete all this. And scroll back up to the top. Let's do 3C in a different color. Let's choose this strange pink orangey color. So this is 3C. Make sure that nobody has any questions. I only have one monitor on me, so I have to keep switching back and forth. All right, so everybody looks okay so far. So this is 3C, and our production rules are S goes to big A, big B. Big A goes to little a, big A, or epsilon. Big B goes to A, B, or little b, big B, or epsilon. So we do the same thing. Here is how we can quickly say that it's probably ambiguous or not. We need to look at what are our combinations of characters that we can have one after the other. So we can see right here that we can have two A's together, so AA. We can see right here, obviously, that we can have two B's together, or sorry, AB together, so AB. Can we have an A follow? I'm sorry, B followed by an A? Let's see. Yes, we can. So I'm going to write that here, and I will show you how to do that in a moment. And then we can also have a B followed by B. All right, so here is how we can get AA. So S goes to AB. This A is going to go to AA. And then we have that B we need to bring down. Let's just have this A go to AA. And there's one way we can get an A followed by an A. Here is another way we can get an A followed by an A. So we have S goes to AB. This A will go to AA. Then we have that B left. We can say this A goes to epsilon, in which case we have AB. And then we can say this B goes to AB, little a, little b, in which case we have AAB. So there's another way we can get two A's together. And since we've shown two ways to get two A's together, we can stop. We don't have to go through the rest of these. You can if you want to. It's generally an exercise in futility. Really no reason to do that. So this language is, again, putting this in caps because it's important to remember that this does not always prove ambiguity. It's just a little helper to show that it may probably be ambiguous or it's probably not ambiguous. So in order to prove that it's definitely ambiguous, we just need to pick a string that we can get, that we can create with these production rules in two different ways. So let's just pick a very easy string, AB. And for these strings that you want to pick, it's going to just be playing around with it a little bit. Some may be obvious, like to me right now, AB is obvious because there's, you can get AB right here, or you can get, A right here and the B right here. It's obvious to me, but if it's not obvious to you, you just want to spend some time with it, play around with some different strings that you can get until you see that there is one that is ambiguous, that is, that you can make in two different ways. So let's make A, B. So we're going to have S goes to AB, big A, big B, and this A is going to go to little a, big A, and then this A is going to go to epsilon, so that gives us little a, big B. This B is going to go to little b, big B, so that will give us little a, little b, big B, B, and then that B goes to epsilon, and that gives us AB. So there's one way. Here's the other way, and it's very easy. S goes to big A, big B. This A goes to epsilon, which just leaves us B. This B goes to AB, little a, little b, and there's our second way. So this language is definitely ambiguous. Thank you for letting me know about the Google Plus logo. I have meant to not write in this corner up here, but I keep forgetting. So let's talk about the language that I came up with when I was doing the office hours for homework 6. I came up with this one language where I was like, oh, this rule will not work. So let me find it real quick. On Piazza, I wrote it down. So here's a language that looks like it's probably ambiguous, but it's not actually ambiguous. So I'm going to scroll down here. I'm going to pick me a new color. How about brown? Does brown show up okay? Let's see. Yeah, that's pretty good. All right, so this is this is one language that our little trick that Dr. Sullivan probably doesn't endorse because of this exact language shows. So this our trick is going to show that it is probably ambiguous, but it's not actually ambiguous. But it is not ambiguous. And I'm showing you this just to make sure that you see that our trick does not always work. It's just a trick. It's just a little tip that Philip asked for. And it's not 100%, it's 99%. So if we have these production rules, S goes to XSY, or you can have 0S1 or ASB, you know, whatever, or YSX, or epsilon, then, you know, you can show that there are two different ways to get this string XY. You could either have X, so S goes to XSY, this S goes to epsilon, which would give you XY, or you could have, so again, this is just a combination, it's not our final string, so you could have XSY, and this X goes to YSX, so that would give you XY, SXY, and there's a second way. So this says, our little trick says that this language is probably, all caps, probably ambiguous. Ambiguous. However, it's not ambiguous. There is no string that you can make in two different ways. So let's say you want to make the string XY. The only way you can do that is say S goes to XSY, and this S goes to epsilon. It's the only way you can make the actual string XY. If you want to make YX, the only thing you can do is say S goes to YSX, and this S goes to epsilon, and that'll give you YX. If you want to make XY, if you want to make the string XY, there's only one way. S goes to XSY, and this S goes to YSX, so we have XY, and then this S would go to epsilon, and that would give you XY. If you want to make the string YX, same thing, S goes to YSX, this S would go to XSY, so that would give you YXSYX, and this S would go to epsilon, giving you YX. And you can keep going if you want to. I'll show you another one. So let's say you want to have XXYY. You would have S goes to XSY. This S would go to XSY as well. So you have XXSYY. This S would go to epsilon, giving you XXYY. There, you can keep going as much as you want. You can keep creating combinations of XY, YX, XXYY, YYXX, I mean, etc., etc. There's no way to actually have a string that you can create in two different ways. So if you're using this tip and it says, okay, this language is probably ambiguous, and then you start trying to find strings that you can make in two different ways and you're not finding one, the rule has not worked. Okay, it just means that the language is not actually ambiguous. So again, this trick will work like 99% of the time, but there are exception cases. So please don't think that, oh, I've done this or I've done this right here and therefore it's ambiguous. You have to find a string, like right here, that you can create in two different ways. Any questions about that? Philip, is that a useful tip for you? Etc. Awesome. So I'm going to put that on our list of things we covered. And so we covered ambiguity. Please let me know if you want more covered. Those are really the basics of ambiguity. So again, if you want anything else covered with that, please let me know. But I mean, that's really all you need to know with ambiguity. So going back up to what you guys have asked me to cover so far, the next thing that you would like to see is Turing machines, and then after that, context-free grammars and Chomsky normal forms. So let's do Turing machines first. So I'm going to delete all this. We'll scroll back up here, and we'll do Turing machines. So a Turing machine is a little more powerful than any of the other machines or automata that we've seen so far, in that usually you have some input, and each of these little blocks represents some character in your string, and you can only read this input from left to right. So you can read this one, and then you can read this one, and so on and so forth. But Turing machines, you can go left to right, or you can go right to left. So it's a little more powerful in being able to check that a language fits a certain form, but because we can go back and forth over the tape. So let's find a good language that we can create a Turing machine for. And Turing machines we did on, was it our last homework, I believe? Let me look. Yeah, we had that awful problem in number 3 with a Turing machine. And then we also had number 4 was also a Turing machine. So let's do number 3, but let's edit it a little bit to make it not so terrible. So here's the language for number 3 in homework. So this is homework 9, number 3, but better, because that one was terrible. We have L equals A to the I, B to the J, C to the K, B to the L, such that, let's make it so that I, J, K, and L must be greater than or equal to 0. And this is Dr. Sullivan's most favorite language. If I equals 1, then J equals K equals L. So the only way that we can read in this language and make sure the string fits this language is using a Turing machine. And so what we're going to have is we'll have our start state here. And basically so I must be greater than 0. This should not be an equal, this should just be greater than. Let me mark this out right here. It's my eraser. Sorry, that was what made it so terrible last time. It has to be greater than 0. Okay, so we need to first start off by reading an A. So for here, and we read it in A, then we just want to mark the beginning of our tape. So we have this tape, it's got some string in it that hopefully fits this form, and we know that if it does, it needs to have an A at the beginning. And what we're going to do with that A is we need to mark the beginning of our tape. So we need to say, okay, if you see this element right here, you know that's the beginning. And the way that we're going to mark our beginning of our tape is just make that A a $sign. So if we see an A, we want to make it a $sign and move right. And I believe this is the notation that Dr. Sullivan uses, but if I'm wrong, please let me know. That's a terrible circle. and I will use whatever notation she actually uses. So from here, we've run in 1A. We can have one of two options. We can either have that be our only A, in which case we need to follow this rule right here, or we can have it we can have more than 1A, in which case we don't care what any of these are as long as they're greater than 0. Let's deal with the easy option first, where there's more than 1A. So if we read an A, we're just going to write X and move right. And we're going to do that for as many A's as there are. A, write X, move right. From there, if we see a B, write X, move right. Do that for as many B's as there are. B, write X, move right. And then if we see, let me scroll over just a little bit here. I'm missing my scroll. There it is. Then if we see a C, write X, move right. Do that for as many C's as there are. C, write X, move right. Scroll over some more so we can have our D. See a D, write X and move right. Do that for as many D's as there are. D, write X, move right. And when we get to the end, which we see as B for blank, then we say B, write B, move right. And that's our except state. So that's the easy part of that language, which, if we have more than one A, we can have as many, B's and C's and D's as we want, as long as they're in order, which this takes care of. So once we've run out of A's, we can only read B's. Once we run out of B's, we can only read C's. Once we run out of C's, we can only read D's. And once we run out of D's, we better be at the end. Otherwise, that language is not going to fit, or that string is not going to fit in our language. So that's the easy one. Now let's talk about the hard one. Well, Sarah's saying that Dr. Sullivan uses this notation. So if you see an A, write $, and move right. So same thing here. A, write X, and move right, etc., etc. And I will, for the second part of this down here, I will write using that notation. I'm going to do the second part in a different color. So this color is the easy part. Let's do the hard part in orange. So the hard part is if we only see one A. So we have our A right here, the one A that we've seen. If we don't see another A, if we go straight into B's, we need to make sure that we have the same number of B's as C's as D's. So that's where things get hard. So if we see a B, we're going to write X and move right into, what number are we on here? We're on Q6. Into Q6. And while we're in Q6, if we see B's, we just need to skip them. And the way that we're going to skip them is we're going to say, if we see a B, just write B and move right. And we got to do the same for all of these. Now it's going to get a little more complicated, and I'll come back and do that. So if we see a C, write X and move right. Skip all the C's from there. This is Q7. If we see a D, write X and move right to Q8. Skip all the D's from there. D, D, move right. And we're going to have to deal with what happens after this in just a second. But I want to come back to Q6, 7, and 8. And also remind you that while we're in Q6, if we're on like the second B that we're reading, for example, we also need to be able to skip over X's. So if we see an X, write X and move right. Same for this one. If we see an X, write X and move right. If we see this, we see an X, write X, and move right. So that will take care of our basic loop so far for if we see some number of B's or X's followed by some number of C's or X's followed by some number of D's or X's. Now we need to implement the part where we make sure all of these are the same. And the way that we're going to do that is we're going to say, if you get here and you've looped through all the other D's and X's and you see a blank, so blank, blank, we're going to start moving left. And this is Q9. And what we're going to do while we are moving left is we're going to say, sorry, this is going to get a little messy here, but not as bad as your homework was. While we just see X's, just write the X's and move left. And if we only see X's, so if we basically have made sure that there's 1A and then all the B's and C's and D's are of equal numbers, if we only see X's, then we get back to our $sign. Let me show you our $sign here on our Turing machine. So we get back to here, right here. Then if we see our $sign, so we've looped through only X's, we saw a $sign, we can keep the $sign and move right and we can accept. Now, our problem comes when we're in Q9, we've looped back over some number of X's, but then we get either a D or a C or a B. That's where we need to say, okay, well, we got to start over. So let's make a Q10. Q10. And this is going to be if we see any of the above. So if we see a B, just keep it as a B and move left. So we just want to keep scrolling left. If we see a C, just keep it as a C and move left. If we see a D, just keep it as a D and move left. And here, we're going to keep moving left until we get to the $sign. So we're going to just loop over those same rules. C, C, move left. I got to scroll down just a little bit. If we see a D, D, move left. And we can still come up with X's right here. So if we see an X, just keep it an X and move left. Now what this does, so if we're in Q9 and we see a B or C or a D, that says that we have not read in all of the characters that are in the string. So that means we can't go all the way back until we get to the $sign and accept because we haven't finished reading the string. So that means we have to go to Q10. And what Q10 does is it just keeps going through all of the characters until we get back to the beginning. So if we're in Q9 and we've gotten to Q10, that means we know we're not done and we don't really care what else is in the string at this point. We just need to know that we're not done yet, so we have to loop back. So loop in Q10 until you see the $sign. And once you see the $sign, we need to go back to where we are just reading in a B. So that is all the way back to Q1. So if you see a $sign, keep it a $sign and start moving right instead. And what that will do is say, okay, now you need to make sure that you have a B followed by a C followed by a D, and you can loop over the extras as much as you want. And you can keep doing this loop here until you get to the point where you're in Q9, you've only looped through X's all the way back to the beginning, and you reach the beginning, there's only X's left, then you can accept. So that is our Turing machine. And unfortunately, I think it's a little too big to fit all on one screen, so I'll just kind of scroll. So here's the start. This green part is if we have more than one A, that's the easy part. This orangish brown down here is the hard part, where I equals 1. So we have 1A here, and then we start reading in B's followed by C's followed by D's. We have to loop. But that's the basic loop. Your homework was a lot harder because all of those could have equaled 0, and that just made it really messy. But that's the basic Turing machine for that one. Let me go back to here. You do not necessarily need a trap phantom. Basically what's going to happen is this is non-deterministic, which means that like if you are, let's say you're in Q3. If you're in Q3, if you read in a B, you have a transition for that. And if you read in a C, you have a transition for that. But let's say you read in an A or a D, you have no transition for that, which means that you automatically go to a sort of trap state and the machine dies. Now, I'm not going to draw the trap state here. You're more than welcome to make this deterministic. And you would have to say, okay, if I'm here and I get a C or a D, then I need to go to trap. If I'm here and I get an A or a D, I go to a trap. If I'm in, get a or a B, I go to a trap. If I'm in Q5 and I get A, B, or C, all little lowercase letters, I go to a trap. I mean, you can obviously see how it makes it much, much messier. So I would not draw a trap, especially in something this complicated of a Turing machine. If you get something much easier on your test for your Turing machine, you can draw the trap if it makes you feel better. But in this particular case, because our Turing machine is already so messy, the trap is only going to make it harder to read. Other questions about that? Right, so this doesn't include the case where A equals 0 because I made it a little bit different on your than what was on your homework, because your homework was like just unnecessarily hard and the Turing machine was really just ugly. So if you look right here, you can see that I wrote, let me try to draw it a little bit better. I wrote right here that everything needed to be greater than 0. Because if you allow all these to equal 0, it just becomes gross. It's really disgusting. I wrote up the solution for that Turing machine in your homework. It's posted on Piazza right now. And I'm sure you are aware because you worked on the homework, but if you're not, you can go and look at the solution and you can see just how ugly it is. So I decided to change it a little bit in this way so that we don't have machine. Just made it a little bit easier on myself, and I apologize to you all for having to work through that ugly Turing machine on your homework. I had to do the same thing, and so I completely feel your pain. It's awful. And I'm very sorry that you had a trap for your homework, Phantom, because oh my god, like I tried to have a trap at first and there was just no way. There was just no way. Any other questions about this, or are there any languages you would like me to do another Turing machine for, or any other questions about Turing machines in general? On the exam, I cannot say one way or another if you need a trap. If it's not an ugly Turing machine like the homeworks were, I would go ahead and put a trap. You know, if it's just a few transitions, then by all means have a trap. On number 4, for example, in your homework, there was a trap. It was a reject state, and even that machine, I mean, it wasn't terrible. It's a little ugly, but it's not so bad that you can't go ahead and put a trap in there somewhere. I just, for this particular number 3, I did not put a trap in. But if you get on your exam a very easy Turing machine, then I would put a trap just to make sure. I haven't actually seen the exam at all. Like, I really haven't seen it this time. And so I'm not sure what kind of Turing machine she will give you. But I mean, if it's just obviously like way too ugly, way too gross, and there's just no way to make it pretty with all of the possibilities of a trap, then don't worry about it. But if you can put it on there, by all means, go ahead and put it on there. All right, so if there are no more questions about Turing machines, then I will tackle what's probably the last topic. We haven't really talked about closure properties at all, which I think, yeah, Phantom, you wanted a proof of closure properties with CFLs. So let's do context-free grammars and Chomsky normal form, and then Phantom, I will do some simple proofs for you of some closure properties for context-free languages. So let's just have a really basic, I'm going to delete all this. Let's have a really basic context-free grammar that we can work with here. So let's have, this was on one of your homeworks, and I'm not sure if you know or if you think this is very basic, but that's okay. L equals a to the n, b to the m plus n, c to the m, such that I believe we said that n is greater than or equal to 0 and m is greater than 0. So a lot of these context-free grammars, you just kind of have to play around a little bit with how to create the production rules, which is really the biggest part of the context-free grammar. So let's have, obviously you look at this language and you see, okay, I need some number of A's followed by some number of B's followed by some number of C's. So let's start with that. So we have S, and S is going to go to some number of A's. So let's make it a big A. And then let's just make the B and C part, let's just make that B right now. And we can deal with that a little bit later. So if we need B to go to big B, big C, we can deal with that. But let's just start with this. And we know, so A needs to represent some number of A's. How many A's can we have? Well, n can be greater than or equal to 0. So A needs to represent some number of A's or no A's at all. So we know that epsilon is going to be one of our possibilities for A. Another possibility for A is any number of A's. We don't really care. And so the best way to do that is just have A go to AA, which means that we can have A's followed by A's followed by A's followed by A's. And then when we're tired of the A's, we want to end them, we can obviously just have epsilon. So we don't even need all of this space, but I will use it. So A can go to AA or epsilon. So that just gives us some number of A's, and I will write that as a side note over here. Some number of A's including 0. Now let's talk about what B can be. I don't know if this is the same color I was using. It is, okay. So B needs to somehow represent, so we definitely need the same number of B's as we had A's. So we need to correct A in some way to give us, so we need to have A to the N, B to the N. So the best way to do that is just to put a B right here. And that will give us, instead of just some number of A's, it will give us some number of A's and B's, and it's going to be same number, including no A's or B's for A. So that will give us A to the N right here and B to the N right there. Now we need to deal with, I'm going to do this in another color, we need to deal with B to the M and C to the M. And we can basically just do the same thing. It's very easy. So we have B from this B right here. And we basically want B to just represent some number of B's and C's, and that number must be greater than 0. So we can't have epsilon, because if we could have epsilon, then the empty string would be in the language, which it's not, because M must be greater than 0. So what are our options? We can have B, B, C, which follows the same logic as this right here, basically saying that we can have M number of B's followed by M number of C's. But we need a way to terminate this, because as it stands right now, this B is going to go on forever. So we have to have a terminal symbol here. And because we need at least one BC, because M is greater than 0, our terminal signal is going to be just little b, little c. And that means we can have, as many B's as we want, as many C's as we want. It's got to be the same number. And when that B goes to just BC, that's going to leave us with something like that. So this part of our production rules will give us, some number of B's and C's, same number, not greater than or equal to, just greater than 0. And so that's your basic context-free grammar there. And that allows you to create any string that goes in this language right here with these production rules. Now what we want to do is number these production rules. And you're probably going to see on the test, she's going to ask you to number them, because she's probably going to ask you to do leftmost derivation, or parsing tree, or what's the other one that she likes to do? Let me see if I can remember it. Oh, the table. So just so you know, and I'm not sure if she's going to ask you for a specific one, but the leftmost derivation and the parse tree and the table are all identical. They're all the same way to do something. So what we were trying to do with these 3 things is we're trying to show that you can create a string that's in this language using these production rules. And all of these 3 things do that. So whichever one, assuming she doesn't ask you for a specific one, and I don't know that she will, but whichever one makes sense to you, use that one if she doesn't ask you for a specific thing. The one that makes the most sense to me is the leftmost derivation. And so I'm going to show you how to create a string using that first. So again, our language was A to the N, B to the M plus N, C to the M, such that N is greater than or equal to 0 and M is greater than 0. So let's create the string A, B, 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 C, C. Okay. And we'll use the leftmost derivation. So I start with S, and my rule 1, and this is how you do the notation for leftmost derivation, says that S goes to AB, and using rule 2 on this A, that goes to A. Oh, I have to number these differently. Hang on. Let me do this a little different. So this is rule 1, this is 2, this is 3, this is nothing at all, this is 4, and this is 5. That'll help us a little bit. So anyway, so if this A, if we're using rule 2, and this A goes to little a, big AB, and we have that B left over, and then we want to use rule 2 again. So we basically need 3 A's, so that's going to go to A, big A, B, B, big B, and then we're going to use rule 2 one more time for this A, and so that's going to give us A, big A, B, 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 big B. And then we can use rule number 3 on this A to get epsilon. I'm going to scroll down a little bit, and that's going to give us A, B, 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 big B. Now we need to get 2 more B's and 2 more C's. So let's use rule number 4. Here's rule number 4 right here. So rule number 4 on that B will give us A, B, 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 big B, C. And then if we use rule number 5 on that last B right there, we'll get A, B, 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 C, C. And that is our leftmost derivation. You can do the same thing with the parse tree. And so that will basically look like you have S, and that goes to A and B. And you can just basically use the leftmost derivation here to create this parse tree. A is going to go to A, B. This A is going to go also to A. Let me put these on different nodes here. A, big A, little b. This A is also going to go to A, big A, little b. This A again is going to go one more time to A, big A, little b, and this A is going to go to epsilon. And the way that you read these parse trees is you basically just go around like this, and you read all of the characters on the end of the, we call them leaf nodes. You read all of those characters. So we have our A, B, 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 and now we need to make B, the big B, into B, B, C, C. So this B is going to go to little b, big B, little c, and this big B is just going to go to BC. And so if you read them all like that, you're just reading the terminal characters A, B, and C, then you will see you have A, B, 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 C, C. So that is the parse tree. And then the table, honestly, I hate, and I hope that she does not give it to you because it's not very intuitive to me. But I will try it for you guys. So the table basically is, it's table of inference, where you have, that is the worst line I've ever drawn. You have a string, and you have a variable, and a reduction rule, and the strings you use to get that string, like so. And let me just flip back and make sure nobody's asking me any questions while I'm going through all this. Okay. And so for our inference here, we want to start with a terminal string. And our terminal string is going to be right here, this BC. So let's start there. So we know that we can create BC because it's right here. So our string that we can create is going to be BC. That's the little c. And we want to say, where did we get that BC from? And we got that BC from this rule where B goes to BC. So it's rule 5. And so our variable that we got it from was B, big B, and our production rule was 5. But we didn't need any strings used, so we can leave that blank. Now, our next string that we can get is we can get, so let's scroll up, we can get AB right here. And we can get a lot of these. So let's do AB. So let's do BC first, because that might be a little more intuitive for you guys. So the next string that we can get is little b, big BC, and that's using the variable b, production rule 4, and we didn't need anything to do that. Now we can combine these two right here to give us B, B, C, C, and that's using variable B, and it's going to be production rule 5. So basically what we did was we took this B and used rule 5 and got B, B, C, C, and the string we used for that was B, big B, C. So that gives us the end of our string. Now let's work on the beginning of our string here. Draw these tables a little farther down. All right, so we know that we can get, using rule 2 here, we can get little a, big A, little b. Little a, big A, little b. And that's using the variable a, string production rule 2, and we don't need a string for that. If we take this a and turn it into little a, big A, B again, we can get a, big A, big B, B. And that's again using variable a, production rule 2. And for that one, we use the string little a, big A, little b. And then we can do that a again, will give us a, big A, B, B. And that's the same thing. We're using variable a, production rule 2. This should be a third B here. And the string that we use for that is this one right here. And that's a, big A, B, B. And then we can use this a and go to epsilon, and that will give us a, B, 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 using a, rule, I believe it's 3, but let's make sure. Yeah, rule 3. So using a, rule 3, and that will give us, so that gives us a, B, 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 and we got that from the string a, big A, little b, little b, little b. And now all we have to do is take this string right here and this string right here and combine them. And I've run out of room at the bottom here, so I'm gonna move over, and I apologize for that. So, but it's our last one here. String, variable, our production rule, and strings used. And so our final string, we're just going to combine, again, this string right here and that string right there. And it's going to be a, B, 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 C, C. And the variable that we can use to combine those two strings is S, and it's production rule 1. Which if we scroll up, I'll show you, is right here. And that just lets us combine big A with big B. So our production rule was rule 1, and the strings we used were A, B, 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 and B, B, C, C. So that's how you would do the table for that. Again, all three of these things, the leftmost derivation, the parse tree, and the table, are doing the same thing. They're just showing how you can build a string that's in this language using these production rules, and that applies to any language with any set of production rules. So that is an example of some basic context-free grammar stuff. Any questions about that before I move on to Chomsky normal form? Okay, so if there aren't any questions about just the basic context-free grammar stuff, I will do Chomsky normal form for you. The hardest thing about Chomsky normal form is just remembering the steps that you need to take. So again, let me delete all this, and I'm just going to work through the example that we have in homework, I believe it was 7. So we have a context-free grammar, and our production rules are going to be S goes to 0 S0 or 1 S1 or A. That'll be A. A. And A goes to 0 A1 or epsilon or 0 1. All right, so again, the hardest thing about Chomsky normal form is just remembering the rules themselves, the steps. And Dr. Sullivan likes to start with 0 here. So step 0 is going to be create a new start symbol. Step 1 is going to be eliminate, I'm so sorry for my handwriting, epsilon productions. Step 2 is going to be eliminate unit productions. Step 3 is going to be remove useless symbols. Step 4 is going to be make long rules variable only. And step 5 is going to be make And we'll talk about what long means here, because it differs depending on whether you're in step 4 or step 5. But anyway, make all long variable strings into length 2 productions. So for step 4, long means greater than or equal to 2. And for step 5, long means greater than or equal to 3. And it's important to remember those two different versions of long, because otherwise you're going to get very frustrated trying to do this. And there's no good way to go about this. The only thing that you need to do is memorize this information. Unfortunately, you can use some sort of mnemonic or something. I don't, whatever you want to do, CEERMM, if you want to somehow create a mnemonic with that, whatever you want to. But you're just going to have to memorize these, unfortunately. So with that being said, let's start with step 0. And we're probably going to have to erase a bunch of stuff as we go through this, because this is kind of a long problem. But so step 0 is create a new start symbol. You can create the symbol to be whatever you want. I think that Dr. Sullivan usually uses G. I could be wrong, but anyway, let's just say G goes to S. And then we have the same things. S goes to 0S0 or 1S1 or A. And A goes to 0A1 or epsilon or 0,1. So that's step 1. Step 2, that's step 0. Step 1 is eliminate E production. So our E production is going to be right here, and we need to eliminate that. So let's start with eliminating it from A. So basically, we need to think about what happens if any of these A's in here, which there's only one right here, but if any of these A's goes to epsilon, what do we have to do? So A goes to 0A1. What happens if this A goes to epsilon? We just get 0,1. Luckily for us, that is already in the rules for A, so we don't have to change the rules for A at all. The only thing we do need to change now is we need to put epsilon in the rules for S, and then we need to eliminate it from S. So we're going to do the same thing. All we want to think about is what happens if these S's go to epsilon. So we can still have S goes to 0S0, or S goes to 1S1, or S goes to A. But now we just need to think, if this S goes to epsilon, what can we have? We can have 0, 0. Or if this S goes to epsilon, what can we have? We can have 1, 1. So we've eliminated that from there, and we just need to put it in G. So G can go to S or epsilon. So that is step 1. Step 2, we will do eliminate unit productions. So step 2, unit productions are where we have like G going to S, S going to A no longer goes to, or never went to anything in particular, so that's really all we have to worry about. So all we have to do is wherever we see one of these unit productions, so right here we have S going to A, we just need to take this A and just substitute in this stuff. So instead, so A is not going to change. So A is going to be still, A goes to 0A1 or 0. S is going to change. We're just going to substitute these two things where we see A. So it's going to be 0S0 or 1S1 or 0A1 or 0,1 or 0,0 or 1,1. And then G is going to change in that wherever we see S in this G, which is just that one time, we need to substitute all of these things right here in for S. So G is going to go to 0S0 or 1S1 or 0A1 or 01 or 00 or 11 or epsilon. Don't forget this epsilon right here. So that is step 2. Step 3 is going to be remove useless symbols. Now, the way that we can remove useless symbols is we basically just want to take the complement of all of the symbols that produce and then all of the symbols that are actually reachable. So let me sort of do both of those at one time, and then I'll show you what the complement means. I'm just reading the questions. Thank you, Phantom, for answering that question. I didn't see it. The chat doesn't automatically scroll down for me, unfortunately. So anyway, moving on to step 3. Again, we just want to take the complement, so we need to find all producing symbols, all the symbols that can be produced. And then all the symbols that can be reached, all reachable symbols. So all of the symbols that can be produced, so we have G produces, and G can produce S right here or right here. It can produce A right here, or it can produce 0, 1, 0, 0, 1, 1, or epsilon. And these are going to be the same up here because we substituted, but S can produce S, it can produce A, it can produce 0, 1, and 0, 0, which we already have right here. And then A can produce A, which is right here, and 0, 1, which is right here. So those are all of our symbols that can be produced. All of the reachable symbols is when you start at the start symbol, which is G, where can you get to? So we can obviously reach G because that's where we start. We can get to S. We can get to A. We can get to 0, 1. We can get to 0, 0. We can get to 1, 1, and we can get to epsilon. And same for this. So if we use G to get to S, we can get to S, we can get to A, we can get to 0, 1, we can get to 0, 0, which are all in there. If we use G to get to A, we can get to A, and we can get to 0, 1, which are all in there as well. So now we take the complement of these two things. Take complement. And what the complement means, in case you're a little rusty from 226, is just that it's just all of the symbols that are in one set but not the other set. And so we can see that there aren't any symbols in the complement. All of the symbols that can be produced are also reachable. So that means there are no useless symbols in this so we can basically skip step 3. If you did have something in the complement, however, if, for example, you could reach T, but T didn't produce anything, or maybe T produced something, but you could never reach it, then you would want to eliminate T, or whatever it is that you could either produce but can't reach, or can reach but it doesn't produce. So no useless symbols here. So let's move on to step 4, which is make long rules variable only. And for this step, long is going to be greater than or equal to 2. Let's look at our long rules. What rules are our long rules here? This one, this one, this one, this one, this one, this one. You're seeing a pattern, I hope. All of our rules are long, so that's not good. So we need to make them variable only, and that's the key to this step. Variable only. So we need to look at all of the rules in here that have things that are not variables. What do we have that are not variables? We have 0, we have 0, we have 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, and 0, 1. So we only have zeros and ones that are not variables. So we just want to make variables for those things. So let's call them, let's see, we already have G, S, and A, so we need to avoid those. Let's call them T, and T is going to go to 0, and let's say V, and V is going to go to 1. And so to rewrite our rules from there as variable only, let's do, so G goes to 0S0, 1S1, 0A1. So G is going to go to TST or TS, I'm sorry, not TS, BSV, or TAV, or 0, 1, 0, 0, 1, 1. So 0, 1 is going to be TB, or 0, 0 will be TT, or 1, 1 will be VB, or epsilon. S is going to go to TST, or let's look up an S, VSV, TAV, TV, and TT, and VB. BSV, or TAV, or TV, or TT, or VB. And then A is just going to go to TAV, or I believe O1 is the last thing. Yeah, O1. So that's just going to be TV. So all we did was we substituted T in for 0 and V in for 1. And we created all of these rules variable only. So we are on the last step, which says make all long variable strings into length 2 productions. And so for this last step, long is going to mean anything that's greater than or equal to 3. We just need to bring it down to length 2. So what do we have that is greater than or equal to 3? We have this. Let me try using my pen here so I can draw better lines. This, and this. And these are repeating, so really we only have, this is step 5, really we only have TST, BSV, B, and TAV. Those are all of our long, for this particular step, long production rules. And we just need to make those into length 2. So the way that we do that is we take, we want to make this and this and this somehow its own production rule. So we need to introduce 3 more variables. So we have GSA and TV. So let's do, we'll do B. I'm going to do it in a different color here so you can see what I'm doing. We'll do B. We'll do this one as C. And we'll do this one as D. It's a D. So we will have, this can be TB, where B goes to ST. This can be VC, where C goes to SV. And this can be TD, where T goes to AV. Now, I've run out of space at the bottom again, so I'm going to write all of our final rules over here on the left. So this is going to be Chomsky normal form. we have start at G, we have S, we have A, we have B, we have C, we have D, and we have T and V. All right, and we're basically just going to sort of copy and paste over here. So G had TST, so TST became TB. So G is going to have TB, that is a B. Or T had BSB, BSB is going to become BC, so G had BC. G had TAV, TAV is going to become TD, so G also had TD. And then all these other rules that G had are already of length 2, so we can just copy those down here. So these rules right here, so TB or TT or BB or epsilon. All right, same thing for S. So S had same things as G except for the epsilon, so we can just copy those all down. S had TB, B, or BC, or TD, or TB, or TT, or BB. A had just TAV and TB, so TAV became T. It's just going to go to TD, or what did we say? TB it had? Yep, TB. TB. B, we decided from over here is going to go to ST. C from right here is going to go to SV. D right here is going to go to AB. And then we decided up here that T goes to 0 and B goes to 1. So T goes to 0, B goes to 1, and that is it. Any questions about that? Let me see. Andrew says, I assume it doesn't matter if you were to select the first two variables rather than the last two variables for step 5 when replacing, or is there a reason for that? So if you select the first two variables instead of the last two, you may run into some complications. So you're saying, right here, if we selected TS instead of ST, then you're going to have something like, you can have, let's choose a different variable. So let's say L, T, and L goes to TS. But you need to figure out how you get to L. And so if you turn this G into, so TST is LT, let's say this one is MV, where M goes to VS. This one is NB, where N goes to A. Nope, sorry, not AB. N goes to TA. Then yeah, that would be fine. I don't think you'd have any problems with that at all. So whichever side you want to choose, if you want to choose the first two or the last two to make into new production rules, is fine. You just want to make sure that whatever production rules you make, you put them in your final production rules here. So I use B, C, and D, and I use the last ones. But if you wanted to use the first two of the variables instead of the last two, then you could do it like that, and that would be okay. So yeah, you can do that. It doesn't matter. It's just completely up to you. Are there any other questions about Chomsky normal form? All right, so step 4, Phantom has a question about. So let's scroll up to, so here's step 4. Let's see what the question is. We can have AO, and that would be fine. Let's see where you are looking at. So remember in step 4 that long means something different than the long in step 5 does. So remember I said that you need to memorize what long means where. So here long means anything that is greater than or equal to 2. And here, we use the same colors. In step 5, long is anything that is greater than or equal to 3. So Phantom asked, can you have A0, which would be, where are we looking here? Do you mean, I'm guessing you mean right here, so TAV would be the only place I think where you have A0. And because you want to make these variable only, and all of our rules are long except for the epsilon rule right here, you want to make all of these rules variable only, so you should not have any, in GS and A, you should not have any zeros or ones in step 4. Does that answer your question? In general, no, because so let me scroll up to a blank spot here. So if you have a rule in step 4, let's just say that you have S goes to A0. Remember in step 4 that long means greater than or equal to 2. So this is 2. So this is considered long. And we want to make this variable only. So 0 is not a variable. 0 is a symbol, a terminal symbol. And so we need to have a symbol for 0 in this step. So we can say t goes to 0 and s goes to a t. And that would be variable only. But anything that's greater than 2, we don't want to have. So if we had, for example, s goes to just 0, then by all means, don't feel like you need to make that a variable, which is, I mean, really that's what we did right here. But if there was no a right here and s just went to 0, then that would just be 1 instead of 2. And then it wouldn't be considered long and you wouldn't have to make that variable only. So to reword your question, is it okay to have a variable and an input in step 4? The answer is no, because if you have those two things, then your production rule is going to be length 2, and that is considered long for step 4. So if there are no other questions about Chomsky normal form, and if there are, please, feel free to write them in the chat or on the Etherpad, and I will answer them. But if there are no other questions, then I will go on to the last thing that I had a question about. Let me see whose question this was. Phantom asked a question about using closure properties for CFLs. So let's do that. You're on board here again. And so this is our last thing that might show up on the exam, and it is closure properties for CFLs. And what you want to do for this one is there are 3 languages that CFSR proved are not context-free, and you just want to memorize. So 3 languages in CFSR and you just want to memorize the languages. They're very easy languages, so not anything too terrible to have to memorize. The first one is L equals A to the n, B to the n, C to the n, such that n is greater than or equal to 0. This is not context-free. Sipser proved it. The second one is L is A to the I, B to the J, C to the K, such that all of these variables are greater than or equal to their variable before them. And that's not context-free. And then the third one is L equals WW, such that W is in sigma star, where sigma is 0, 1. And that is also not context-free. And that is actually very similar to the language we talked about at the very beginning of this video. And you can prove that all of these are not context-free using the pumping lemma. And then you can also use these languages with closure properties to prove that some other language that looks kind of like these languages is not context-free. So let me give you an example here. Let me see. So context-free languages are closed under Sorry, I have a lot of windows open. All right, context-free languages are closed under substitution, concatenation, union, and star. So substitution, concatenation, union, and star. And so you can use these 4 closure properties along with these 3 languages to show that these 3 languages to show that a language is not context-free, or you can use these 4 closure properties along with languages that you know are context-free in order to show that a different language is also context-free. So let me give you some examples of both. So I'm trying to think of an example that would work very easily here. Let's say that we have this is easy. We just went over this, and I proved to you that this language was context-free a little earlier in this video. So if our language is A to the n, B to the m plus n, C to the m, such that n is greater than or equal to 0, and m is greater than 0. Sorry, I always want to write equal. Greater than 0. We want to prove that this is context-free using closure languages. Then what we can do is use concatenation. So if we have a language that is A to the n, B to the n, such that n is greater than or equal to 0, and you can prove that's context-free. You can, create some sort of machine to show that you can, or you can create a context-free grammar to show that this is context-free. Anyway, we'll call this L1. So L1 is A to the n, B to the n, and you can prove that's context-free. And in the same way that that is context-free, L2, which may seem obvious to you, B to the m, C to the m, such that m is greater than 0, that's also context-free for the same logic there. And so if you take L1 concatenated with L2, L1 and L2, then that's going to give you A to the n, B to the n, B to the m, C to the m, which is the same as A to the n, B to the m plus n, C to the m. With these rules here, n is greater than or equal to 0, and m is greater than 1. So n is greater than or equal to 0, and m is greater than 1. I'm sorry, m is greater than 0. And so that is proving that a language, this language here, is context-free using closure properties. You can say it's closed under concatenation. These two languages are context-free. If I concatenate them, I get this language right here. Therefore, this language is context-free. Now, let's do the same thing, but to prove that a language is not context-free. So that's where you use these languages up here. And mostly what you're going to do is you want to substitute in some way to get whatever language you're working with to look like a language up here. So let's say that we have let me think. There was one, so the one that you had on your homework, I'll do that one because that one's I remember very easily. The one that you had on your homework was L equals 0 to the, we'll say n, 1 to the 2n, 0 to the n. You don't even have to call them all n. Let's say 1 to the 2m, 0 to the p, such that so n is less than or equal to m, and we have to say that p is greater than or equal to 2m. And the reason I put those restrictions on it is because we need to get this language right here to look like this language right here. And so we just need to use substitution. So here's our substitution. We need it to look like this language. A to the I, B to the J, C to the K, such that 0 is less than or equal to I, is less than or equal to J, is less than or equal to K. Okay? We need it to look like that. So let's just use some substitution. If we say A equals 0 and I equals n, that takes care of this one. If we say B, so this is the only tricky part about it. If we say B equals 1, 1, and J equals m, then we are still getting 1 to the 2m if we say B to the J, because we have 1, 1 to the m instead of just 1 to the 2m. So it's the same thing. Then if we say C equals 0 and K equals P, and you may say, wait, we have two things that equal 0. It really doesn't matter, what these variables mean. We're just substituting. So, A can be anything, B can be anything, C can be anything. We're just making them these specific things so that the language looks like this when we're done. So if we rewrite this language using this substitution, then we will get L equals A to the I, B to the M, oh, no, sorry, not M, B to the J, C to the K, such that, here's our rules. N is greater than or equal to 0, so that becomes I. M is greater than or equal to N, so that becomes J. And we needed P to be greater than or equal to 2M, And so our P is now K, and K must be at least twice this number. So I'll write this out for you. K is greater than or equal to J. And since J can be equal to 0, K can be, also greater than or equal to 0. It could be equal to 0, so we can just rewrite that as 0 is less than or equal to I, is less than or equal to J, is less than or equal to K. And since SIPs are proved that this language right here is not context-free, then you can go and say, because context-free languages are supposed to be closed under substitution, I did some substitution, I got this language that was not context-free, therefore there's no way this language could be context-free as well. Questions about that? Sam wants me to go through the 3 languages in CFGs again, so let me do that. So here are the 3 languages in CFGs in the light blue color here. So number 1 is just where you have an equal number of A's, B's, and C's. And really all you need to remember is that you cannot count an equal number of more than 2 things in a context-free language. Cannot count equal number of more than 2 symbols in a context-free language. You just can't do it. And so you can have A to the N, B to the N, and that's fine. But once you add in the C, it throws you off because there's just no way to count using context-free grammars these 3 symbols so that you can show that a string is in this language. So that's that. Number 2 basically does the same thing. So we have 3 symbols, and they don't necessarily have to be equal this time, but we still need to count and make sure that this symbol is at, somehow less than or equal to this symbol, is less than or equal to this symbol. And so, for number 2, it's sort of the same thing. There's no way to count these 3 different symbols using a context-free grammar. If we could somehow relate the I and the J and the K in a different way, like if we had J equals I plus K, then that's fine. We can count that because really all we're doing at that point is counting the I's and the K's and just making sure that we have I plus KB. So that's fine. But when we have these 3 symbols, unless we have some bigger restrictions on them, like if we said J equals 0, we could count that very easily, obviously. There's no other way to count these 3 symbols unless you have some restrictions that relate them like this. So if you had a restriction where J equals I plus K, you would basically get this language right here. That's basically the same thing, and you can prove that that is context-free. But without any really specific relationship between these 3 variables, there's nothing you can do to count them. And then number 3, again, we showed this for the pumping lemma. When we first started this, it was very similar to this. It wasn't the exact same thing, but it's very similar. We showed that this is not context-free. So this is just saying, number 3 is saying you have some W, which is in sigma star, and sigma is going to equal 0 and 1. And you just want to repeat that W. So you have W followed by W. And they need to be the same thing. So you have some string followed by, let me move some windows around here, followed by W. by the same string. And we proved this with the pumping lemma, that this is not context free, because if you start deleting things out of this W and you can't delete them out of this W, then you're running into problems, or vice versa. You may have some issues with that. Other questions about, let me see, so are we able to change the range of the variable to get it as close to CFGs? So you can't change the range necessarily. You can do logic on the range of the language itself. So down here, I just knew that this had to be greater than or equal to this, because that's what this language is ultimately going to be. And because all of these things can equal 0, then I can say, since k, which equals p, can be equal to 0, then I can say, k is greater than or equal to 2j, and since this can be 0, this can also be 0, so k must be greater than or equal to 0. You could also do right here, if you wanted to, you could do b equals 1 and j equals 2m, and that would do the same thing. Then you would have b to the j as well, and you wouldn't have to go through this logic at all. You would just get this right here. So there's that. So don't change the range of the variables themselves. Just do logic on the range. Try to substitute them in some way in order to get them close to what CFGs 3 languages look like. Andrew asked, you don't think she's going to throw in any inverse or general homomorphism closures, do you? I don't think so. She generally does not hate students when they're taking tests. And so I would not worry about seeing something like that. She wants to know that you understand the basics of the ideas themselves. And so, she's not going to ask you to do anything really complex, unless that's something like if she were teaching a unit on general homomorphism, then obviously she would ask you about that. But no, in general, I don't think that she would ask you anything that hard, unless she was actually teaching it. Phantom said the homework problem was slightly different. Let me see. Let me see if I can actually see the homework problem. I think that was on homework 5, maybe? Let me look it up.